Well, hello and welcome to Math 212. We're going to be looking at patterns and functions today and discussing relations as well. In our elementary school teaching, what we are doing is looking at these patterns so that students can develop the ideas of functions later on in their math career. And if you can show them how to look for patterns, it makes their algebra so much easier. So here we are talking once again, driving home. We're going to be looking at patterns and functions and relationships. It's important for our elementary school students to understand this relationship between numbers and pictures and look for patterns and to see what's going to happen next. And they note here that they talk about making predictions for these generalizations as well. So here we have tiles, and we're going to figure out what's going to happen next. And that's the point of this, is what's going to happen next. After reviewing this and going through, I note that, let's see, I'm looking here, and that's a 1. This is 2 times 2. This I can see is 3 times 3. So I think this is going to be 1 squared, 2 squared, 3 squared. I'll bet you this one's going to be 16 because it's going to be 4 squared. This will probably be 25. 5 squared, and I don't have to draw it because I looked for patterns. Besides that, I don't want to keep drawing these, and I especially don't want to draw one that's a 20 by 20 because that would be just way too much. So I'm going to say that this is whatever my number is, and we're going to call that n, so I'm going to say that's n squared. The number of white tiles, well, see, that's a little different. The number of white tiles, though, kind of goes all around these edges, so it looks like 4. This one is 4 times 2 because I see that there's 4 sides there. Well, that is kind of nice. That's 4 times 3, 4 times 4. I'll bet this is 4 times 5. And this, of course, the next one would be 4 times 6. So I think what's going to go on is it's 4 times whatever my n is plus 1. And then the total is just going to be, total just means to add, so that's going to be n squared plus 4 times n plus 1. And that's me looking for patterns and then developing a pattern using that n and not having to draw out a 20 by 20, which would be a pain. All right, here's another little fun one where we get to look at these squares, and we're going to figure out just exactly, with relation to n, we're going to figure out how we can write this so we don't have to draw one that is like 50 in length. Figure out how do we get these answers. So how many little squares is this? Well, if n is 1, I've got 1. If n is 2, I have 3. This would be our n. If n is 3, I have 1, 2, 3, 5. If n is 4, I have 7. 9. Okay, I've got the pattern. Okay, so that's nice. So now I have to figure out a way to come up with, how do I say how many I'm going to have with using this n, so that if I say, well, okay, you're going to make one that is, let's say, 50. So like 50 tall, so it would be like 50 this way. And then it would be 50 this way. But this guy gets counted twice, so it's always one less. So they get counted twice, but it's one less. So it would be 2 times whatever your n is minus 1. Now that's my guess for this. So I'm going to see if this works. Because in making patterns, it is kind of like a little, you look for the pattern and then you kind of guess and check. So for this one, I look at this and I say, okay, if n is 1, do I have 1 there? And I did. If n is 2, 2 times 2 is 4 minus 1, and I do have 3, good. And if n is 3, 2 times 3 is 6 minus 1, and I have 5. So you see all of these are checking out, and this would be my generalization for this particular pattern. So being able to see how this pattern changes with changing n and being able to describe that is just saying, well, the number of little squares is going to be 2n minus 1 is very important in helping students learn about functions. This slide is reiterating the fact that elementary school children don't necessarily investigate functions, but they do at a conceptual level, maybe not at the level of working with the variables like we just did with those squares, but understanding what's happening. And understanding these kinds of patterns and how they develop only helps students and aids in their understanding of algebra and mathematics at a higher level, which is what I call a door opener for students. The more you can understand math, you don't necessarily have to go into a math field, but it opens doors of opportunity and allows them to go forward with their education if that is what they choose. Now, just as a reminder, in case you might have forgotten what a function is, a function, we have one set of elements, say 1, 2, 3, 4, and another set, we'll call this the domain, and we're mapping our functions from one set to the other, 2, 3, 4, we'll do like this. And as long as we can say that, we'll just do something like this, as long as each element in X goes to exactly 1 Y, then we say that we have a function. Another way that we did this was we did something called a vertical line test, if you'll remember in our algebra classes. So we had a function like this, and we said as long as it passes a vertical line test, meaning for each x he only goes to 1 y, then we say that we have a function. And it doesn't matter that both 3 and 4 went to the same number. Oops, sorry about that. What matters is that each x goes to exactly 1 y, or each element in the domain goes to exactly 1 element in the range. And that's what makes our function. And here's an example that's kind of near and dear to all of us. If we're working for an hourly wage, there is a functional relationship between the number of hours worked and how much money that you get. So that is a definite function relationship. And looking at this particular table, if we were to let x equal number of hours worked, then we would say your pay equals 8 times x, and this particular table follows that function relationship. In elementary school, you might need to introduce the concept of a function using a function machine. That's one of the ways that we have elementary school students look at functions, and we call it "What's My Rule?" is the name of the game. And some students really enjoy guessing what the function is or what the rule is. And here's an example of an x plus 3 as our rule. And you can write it like that if you would like to, just to kind of introduce them to the topic, not necessarily test them on it, but to that topic. And here we are writing that rule as x plus 3. Now, function notation is very precise. In this particular case, we're looking at some sort of f of x equals x plus 3. And if you'll remember, in place of x, we put a 3. In place of x, we put a 4. In place of x, we put a 10. We say this as f of x, meaning f is a function of x, and we would put that number in for x. As you go forward with this, you can make the rules a little more complicated. Here's one where your rule is 3x plus 1, and of course, in mathematics, it's always, to me, as though we walk, we do an x plus 3, and then we do an x plus 7, then we do an x plus 4, then we do a 2x, then a 3x, and then we get faster and faster until we make them harder and harder. And here's one where it's made it a 3x plus 1. All right, in your homework, you have a greatest integer function problem. So I just wanted to talk about what a greatest integer function. Here's an example of one. I'm going to use the birthday one. That's my favorite example of greatest integer function. So this is your birthday. Let's pretend as though we have this, let's say a child. He was born in the year 2000. And let's say this is 2001, this is 2002, 2003, 2004. And your birthday and how old you are is an example of a greatest integer function, because all throughout the year, when you're first born, let's say you're born in 2000. Well, I wrote 2001 there. Say you were born in 2000. All throughout that year, you are 0 until the day of your birthday. And when that birthday comes along, then you are then 1 year old. And you stay, look at that crazy thing. Hold on. So you stay 1 year old until your birthday again, at which point you become 2 years old. Notice the open circle here because it does pass a vertical line test. So all throughout the year, you stay 2 until your birthday. Same thing whenever you go to hit the age of 21. They will not let you, even though you might say be 20 years and a half, and it might round up to 21, that doesn't count. You're not 21 until the day of your birthday. Likewise, on these values, you are 3 years old until the day of your birthday, at which point you turn 4. And that's one of my favorite examples of a greatest integer function, because it does happen to deal with a birthday, which is always fun. All right. So if you have any questions with your homework, you be sure and send me an email. And thank y'all for listening. Have a great day.